Today, we are breaking off the shackles of ugly solutions, we are straightening out our pipelines, and we are setting our system to embrace all the juicy mechanics we gathered along the way, labeling them as technical debt for better times. Yes, we change our skeletal animation framework. Again. But before we start, I must actually correct some past mistakes. It turned out I lied to you in the first video about skeleton modifiers. The picture with their performance is not so bright, and an attempt to measure it by looking at physics frame processing time is cringe. They are processed in different thread or in different time, and their processing is unbound from physical frame processing. To measure it, you will need to use the profiler and then look at your process modification method's execution times. This breaks some hopes and probably pushes potential big games toward using skeleton modifier frameworks for main characters and bosses, and usual animation player or even some direct vertex animation shenanigans for default enemies. Processing time clearly is proportional to the amount of modified bonus. For example, to animate a character of our tutorial series, my computer thinks for about 0.3 seconds. The bigger skeleton on the right is animated in about 0.5 seconds. This is my processor, so you can eyeball the execution times without downloading the project by comparing your PC specs to mine and by comparing your skeleton to Mixamus 1. Now, I really want to sell you the skeleton modifier idea, but I don't sell snake oil, and as a good faith agent, I first need to warn you of potential downsides of using them as your main framework. Skeleton modifiers are a low-level-ish approach to animation, and that affinity is the source of both positive qualities and possible drawbacks. Firstly, every single line matters. You want to understand 100% of your programs by default, but sometimes you can be lazy and get away with like 90% of understanding what exactly happens, especially if you modify someone else's work. With direct bones modification, this won't fly. You need to understand every single character. This function is executed about 6,000 times per second, and the smallest mistake, the tiniest bit of misunderstanding, will turn your character into eldritch abomination. It is also unlikely that this approach will become super popular, so there won't be a lot of sources to get inspired. You also won't be able to skip developing any feature you want, but don't want to develop. Default here is empty page, nothing, so if you need to add a feature, most likely you will need to develop it. Okay, now, what is our payoff for such a weight on our leg? Well, you can do anything, like literally any motion and or behavior you can imagine. If you can describe it, you can make your skeleton do it. Synchronizing your leg cycle during blending from running animation into sprinting animation while your right hand and torso smoothly follow mouse cursor and left hand plays an independent animation of throwing a grenade, what have you. We are also immune to a number of problems Animation 3 suffers from on large-scale projects, such as lack of transparency and supportability, request hell on complex framework transitions, and the limited ability to snapshot. I talked about transparency in earlier videos, I will talk about request hell solution in this video later, and right now I want to discuss snapshotting. This is one of the main selling points for this system if you want to create a game with robust multiplayer environment. Don't even get me started on Godot's default networking solution. I talk about big boys toys like dedicated authority server with client-side prediction and later reconciliation. As our system literally executes code each frame and is powered by a finite list of parameters, we have the full power over what we do with them. For example, we can photograph each parameter, each frame, and store some amount of latest snapshots sorted by time. Or, if requested, we can reverse the system to some previous state. If we really want, we can even calculate a non-existent before state by interpolating between two neighbor snapshots. Do you get it? Imagine you use some 20 nodes blend tree and suddenly your server tells you, we had a mistake, so unblend the last 0.5 seconds, you then turn to the different transition route and calculate from there 0.5 seconds forward. You will be sitting there dumbfounded, trying to imagine what the fuck the words unblend the transition mean. But I, as a skeleton modifiers enjoyer, will be like, yo, unblend the blending? You mean animation progress minus equals 0.5? I mean, it's harder than that. But you get the idea. If your dream game has ambitious multiplayer, I recommend you to at least consider skeleton modifiers. Now, in my favorite approach, instead of showing you one example of how to do things and Calling it a day, I will teach you how to write all skeleton modifiers in this world, and then I will illustrate it by an example. At the heart of every modifier you can find a simple structure. First, you define some collection of bones, be it a sub-hierarchy of your skeleton, random selection or a single bone. Then, for each of selected bones you set either its rotation or its position, or probably both using Transform3D. And you can set those parameters with a number of different functions that can add some flavor. Often, you will want to modify a lot of bones at once, and even more often, you will want to use an animation to store some poses data. So, how to marry an animation with your skeleton transformations? Well, both skeleton and animation have similar structures. They consist of pieces that can be described as an integer value that is used as an ID for internal methods, and they can be described with a string-ish parameter that is more suitable for mid-sex to talk about. Animations consist of tracks, track has an ID, and track has a field of type nodePath, which is a glorified string with some self-awareness. Skeleton consists of bones, bone has an ID, and a string that represents bone name. So to put this data together, you will use a for loop that is either based on tracks or on bones, depending on what you like more. And then you will use several special getter methods to translate human-readable descriptions of tracks and bones to integer IDs and back. These methods are on the screen. And another little info bit is that animation tracks in fact aren't fully defined by their nodePath. They also have track type. There are a bunch of them, but for skeletal animation we mostly use position tracks and rotation tracks. Finally, when you learn how to restore bone index from track number and vice versa, you can assemble your bones transform. Transform3D consists of two paths, origin and basis, i.e. position and rotation. Position data comes from type position 3D tracks. Rotation data comes from type rotation 3D tracks. And to get this data from a track, we use the track type underscore interpolate method and feed to it the progress of an animation we want to know. It is important to know that progress can be any number. The word interpolate here means that we can imagine what this value would be if we had a key right here, but we don't need that key to exist. To consolidate, let's read together the function that takes bone index, animation and progress and returns us the transform of this bone according to the animation. First we create a variable to return, that's a given. Then we search for a position track by turning our bone index into track path. If returned number is -1, it means that animation we search doesn't contain such a track at all. For example, that bone doesn't move in this animation. In this case, we do an equivalent of do nothing instruction by setting transform's origin to the origin our bone already has, i.e. we don't touch it. If we found a track, we interpolate the value from it using progress. And then we do the same with rotation. The only small difference here is typecasting, because animation stores rotation data in quaternions, but Transform3D stores it in basis vector triad. And we return our transform. So far, nothing scary, right? Well, this is kinda your gameplay to work with modifiers. Select bones, define some rules. This is principal usability. Now let's discuss what I did to make this into world domination device. One of the biggest problems for animation trees is request hell on complex transition. Your system is defined by a shit ton of parameters. All your nodes are different, some it double, some it boolean, and some take some strange string request, etc. I want to transition with a short and clear to understand call, and by clear to understand I don't mean a bunch of ugly requests masked by a helper function. If you watched my previous Skeleton Modifiers video, you remember me proposing an umbrella class that will practically be a transition node analog from blend tree. But now I think I invented something better. If I've got a nickel for each time I found an unconventional use for AnimationPlayer, I would have 2 nickels. It's not much, but it's strange that it happened twice. So, imagine we have here some respectable amount of modifiers, for example 10. The most important parameter in modifier is influence. If you want to slowly enable modifier, you slide influence from 0 to 1 over some period of time. Moving influence from 1 to 0 makes a modifier obsolete. So, in each situation, you have your ideal set of modifiers, and then bam, someone asks you to transition to some other set of modifiers over 0.2 seconds. If only we had a node that can smoothly change a bunch of numerical values over time and automatically do all the blending for us. Yes, we play settings for our system. It's like you have a huge audio pult and a bunch of photos of it with different sliders position. At any given time you can give a photo to your pult operator and they will slowly transition your audio settings from the current template towards your new inputted one. So how it works is I have here animation that have tracks for influences of these modifiers, and then on enter state I tell my settings animator to play the needed settings template. And because this is quotes a purple node, it guarantees me that inside the frame this thing executes before the first skeleton modifier does. But here's another puzzle piece. This meta modifier I use for optimization. I don't really understand why, but skeleton modifiers are processed even with influence that is equal to 0. It means if we have here like 10 modifiers with only one truly working, then 90% of the work we do is just thrown out of the window, because zeroed modifiers take calculation power but don't have any effect. So here as our first modifier I run a short function that disables zeroed modifiers and enables ones that have any other value. The more modifiers we have in the system, the more performance this code saves for us. I actually have an example. I don't have here any real IK works, etc. The only modifier I prepared for this episode is a simple animator that can also take a whitelist mask. Here we have 3 of them, one for full body, one for torso and one for legs. And only as an experiment here I made it so all our moves are animated by a full body modifier except our sprint action that is animated by torso and legs animators being played simultaneously. So if I disable the meta modifier and run, I can enable profiler, and what I will see here is it took my system 0.6 milliseconds to run my modifiers, and it always runs all 3 of them despite most of the time only full body modifier being enabled by influence. Now if I enable it back and run again, you will see that most of the time I use one modifier, sometimes I use 2 if I sprint, and I use all 3 only during the moments of active blending between 2 settings templates. And my system performance is much better because I don't do empty calls. Now the last thing, you will see this construction, or rather this class of problems often. Imagine we are in the moment of transition and we had some pose A previously and we want to go into pose B after let's say 0.2 seconds. And then let's look at the middle of that transition. If both pose A and pose B are implemented via one modifier, it means that our settings animator doesn't do any blending at all, and we need to blend our poses solely by the code of the modifier itself. However, if pose A was created by modifier A and pose B is created by modifier B, then we blend by modifier to modifier transition. In this case, we need to switch in modifier settings immediately and play a full B pose from the start. Otherwise, at the middle of the transition, we will have a blend of 0.5 of pose A because we blend out modifier B, and then on top of it, we will have 0.25 of pose B because pose B double dips blending by being blended in both inside modifier B and by modifier B having 0.5 influence. This non-full pose will look strange and will ruin your transition. The right approach is to branch. If we do pose-to-pose transition inside one modifier, we use one blending mechanism, and if we do modifier-to-modifier transition, we switch in modifier poses instantly. By the way, remember the umbrella transition node I shown earlier? The same approach. If true transition happens, we mix modifiers but not settings. If no transition happens, we mix settings. Finally, you probably want to see the full code of an animator, right? So first we have a bunch of variable declarations. Disclaimer, I have no idea if it helps or not, but since we do low-level stuff, I decided to embrace this basic ESC style with declaration in the start of the file, and then I only juggle these predefined variables. I am not competent enough. If you know how memory allocations, heap, etc. works in Godot, feel free to teach us all in the comments. What are those variables? First we have animation stuff. We always have current animation, and if we are in the process of blending towards something, we also have previous animation defined. Animation also can be cyclical to linger infinitely, and each animation needs a variable to count progress for data interpolation. To blend between animations, we use boolean flag for execution routes, and then the main variable here is blending percentage. If 0, then we are full previous animation, if 1, we play full current animation. we calculate blending percentage by knowing the time over which we blend and counting the progress of the process. And we count the time each frame by comparing current time and the last modifier fire timing. Be aware that I lazily use current time as system's Unix time in milliseconds, just as I do it for my model states. If you want to have a pause in your game or some time coefficients or to be immune to system time change attacks, you will need to create better time calculation method. These variables are for algorithm usage. When we prepare our node, we make sure both animation fields are filled with do nothing animation. Then, for now, our animator has only one instruction: play next animation. The idea is stolen from default AnimationPlayer. If we want, we can set the blending time. Here we have a small idiot-proofing fence to get rid of negative blending time requests. Then, if no blending needed, we simply push current animation values into previous animation variables and set current animation as inputted. If blending transition is requested, we also set some blending variables. Okay, each frame, first thing we do is we manage our time awareness. We do it by calculating the delta between now and the last call. We then add this delta to our animation progresses, and if animations are cycling, we undergo a cycle switch. After that, we manage our blending variables. We use the delta time value we just got and add it to blending time counter, and then we update blending percentage value. If you understand that we blend longer than required, that means we did all we needed and we can stop the blending process. Finally, everything is prepared to bend some bones. First thing we see is this funny construction. It works because in GDScript this parameter in for loop syntax can be many things, and we abuse this fact by making it a collection of integers if we have a whitelist export field defined here, or if not, in other words, we work on the whole skeleton. We make this variable into a single int value that represents all bones of the skeleton. And then, no matter what happened before, we iterate over some collection. For each suggested bone, we first calculate its pose according to the current animation and its progress. If we don't blend, that's our work for the bone. If we do blend, we need to also calculate this bone's pose according to the previous animation and its progress, and then interpolate those two transforms via blending progress value. And this function I already explained before. And the whitelist. So it will be immensely helpful to be able to have here in export fields a widget that works like bone filters for blending tree, but we can't. So what I did is I created a resource that has nothing inside except an array of integers, but it is done as a resource so I can better use it in export fields, because exporting arrays and dictionaries is a pain in the ass. I also gain an ability to save and load these resources instances, and I use it because I generated those torso and legs masks programmatically, saved them, and then pulled back from the file system. Ta-da! This episode exists thanks to these wonderful people who modify the amount of meat on my bones, so salute to them. Today we discussed only the simplest incarnation of skeleton modifiers. In the next one, we will make them do some inverse kinematics for us to fix our ledge traversal animations. But from now on, as we fully transitioned to skeleton modifiers, I expect to use them to their fullest. This will be a wild ride. See ya!